Good morning. Here we are again. We're about to start the third in a series of videos on integration and applications. This is the third of three, and this one deals with how do you calculate areas and volumes using integration. So without further ado, let's jump right in. We're going to first start with finding areas on the curves. If you look at that first curve I have there, y is equal to some f of x. And above that I'm trying to find the area bounded by the curve. Y is equal to f of x, the x-axis, and the lines x equal a and x equal b. So that the area that I'm trying to find has to be bounded on all sides. It's bounded on top by the curve. It's bounded on the bottom by the x-axis. It's bounded on the left by the line x equal a. I want to draw that in now. All right, vertical lines have equation x equal a, at least that particular vertical line. And I'm going to draw another vertical line further to the right. And that vertical line is x equal b. Now you can see the area starting to take shape, right? This point here is x equal a, and that point is x equal b. So let's read it again. The area bounded by the curve y is equal to f of x is bounded on top by the curve y is equal to f of x. The x-axis is bounded on the bottom by the x-axis and is bounded on the left by the line x equal a, and is bounded on the right by the line x equal b. So we're clearly talking about this shaded area, or the shaded region here. And the question is, how do you find the value for such an area? Well, without lamenting the point too much, the area is found by integrating. You're going to integrate the function that represents the curve, and you're going to integrate between the lower boundary on the left, which is a, and the upper boundary on the right, which is the b. So that area, the exact value for that area, is given by this expression shown there. Area is equal to the integral between a and b of f of x dx. All right. Now, almost exclusively, all these areas will be areas that are above the x-axis and in the first quadrant. Right? Later on, when I do the other three videos, which would be exclusively for the Pure Math Unit 1 people, you have all kinds of different areas to find. Well, we're going to start off with these relatively simple ones, where you simply find the area bounded by the curve, by a curve, the x-axis, and two vertical lines. So that's the formula, and we're going to use it to our advantage. All right. There. Let's look at our first example. I'll actually write what I'm supposed to be finding there. Give me a minute. Let me format stuff a little bit here. Okay. Clearly, this first area they're looking for, let me write it out in words. Find the area bounded by the curve y is equal to 2 root x, the x-axis, and the lines x equal 1 and x equal 4, which is clearly that shaded region there. How do you find that area? Well, we just saw that it's based on an integral. That area, I'll call it A, is equal to the integral between my limits. Let me write the generic thing first. A and B of f of x dx, which in this case will be the integral between, well, what are my limits? The lower limit is 1, the upper limit is 4, and the function is 2 root x dx. Well, how do you integrate that? That's 2 times, and root x can be written as x to the half, right? Okay. Oops, I forgot my limits, 1 and 4. If I integrated that, I'll get 2 times x to the power half plus 1, which is 3 halves, divided by 3 halves. And we'll evaluate that between 1 and 4. I'm going to flip the 3 halves and get 2/3. So that's 2 times 2/3 times x to the 3 halves. Evaluate it between 1 and 4, which is 4/3 times x to the 3 halves. Evaluate it between 1 and 4. Okay. Now I can leave out the 4/3 because I don't have to plug anything into that 4/3. That's just a number, 4/3 into, and then I'll plug both limits into the x to the 3 halves. So that will be 4 to the 3 halves minus 1 to the 3 halves. Right? I like to do it that way. I know, technically speaking, you should plug in the, not you should, you could plug in the upper limit into the entire thing. So that would be 4/3 into x into 4 to the 3 halves minus 4/3 into 1 to the 3 halves. Well, if you look at that, 4/3 is common, which you could factor out. So I decided to factor it out from the beginning, right? So you can do that. As long as it's a constant, you can factor it out from the beginning and just plug your limits into the variable part. Okay, this becomes 4/3 times, now what's 4 to the 3 halves? Well, that's root 4, which would be 2, and 2 cubed is 8. And 1 to the 3 halves is just 1. 8 minus 1 is 7. 7 4 is 28. So the answer is 28/3, whatever units, squared. And that's the exact value for that area that's bounded there. Okay. That takes care of the first one. Let's look at the next one. We're going to write what they're asking for, or they should be asking for. I'm going to copy and paste this. I just have to change the limits in the function. There. Copy. And insert here. Insert it there. You don't want to be inserted. There. In the second example, we're finding the area bounded by the curve, and it's a different curve. Y is equal to x minus 1 all squared plus 2. The x-axis and the lines x equals 0 and x equal 2. Yeah, 0 and 2. There. Let's find the area bounded by the curve. Y is equal to x minus 1 all squared plus 2. Between x equals 0 and x equal 2. So this would be x equals 0 there and x equal 2 there. They're talking about that region. How do you find that area? By integration again. So let's see how this goes. This area will be given by the integral between 0 and 2 of f of x dx. That's the generic expression. And therefore the area is equal to the integral between 0 and 2. The f of x function is x minus 1. All squared plus 2 all times dx. Okay, how do we integrate that? All right, a couple of ways you could do it. X minus 1 all squared is not difficult to expand out, so we can do that. Or we can leave the x minus 1 all squared as it is, because you remember, you should know how to integrate a function in the form, a function of the form f of x to the n, where f of x is linear and n is not minus 1. So we'll try it both ways, just to show the flexibility. So let's see. I'm going to keep it as it is. When I integrate x minus 1 all squared, which is in the form f of x to the n, f of x is linear and n is not minus 1. The result is 1 upon f prime. F prime means differentiate what's in the inner bracket there. So when I differentiate that, I get 1. 1 upon f prime into f of x, x minus 1 to the n plus 1, which would be 3 upon 3, like that. And then plus integrate the 2, I get 2x. And this entire thing, I have to evaluate between 0 and 2. Okay, so if I plug in my upper limit, I'll get 2 minus 1, which is 1. 1 cubed is 1, so that's 1/3 plus 2 times 2. That is my upper limit. Here is a key point to note. When the lower limit is 0, do not assume, I repeat, do not assume, I repeat, do not assume, I repeat, do not assume that when the lower limit is 0, you will get 0. Always, 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 always check it. Did you hear me? Good. So let's plug in the 0, and as you will clearly see, you will not get 0. You will get 0 minus 1, that's minus 1. Minus 1 all cubed is minus 1. So this is minus 1/3. And of course, the second piece, 2 times 0, that's 0. But the entire thing, the entire lower limit when substituted does not give you 0. So be careful with that. Okay, so let's see what this gives me. 1/3 and 1/3, that's 2/3 plus 4. That's 4 plus 2/3. 4 is 12/3 and 2/3 is 14/3. So the area is 14/3 units squared. I'm going to check this against the other method I could have used in what may I? Let me do that. What? All right, never mind this. All right, let's try this again. There. Okay, let's try the other method of expanding our brackets first. See how good our integration is. See how flexible we are. The area was given by the integral between 0 and 2. Method 2. Area, integral between 0 and 2 of x minus 1 all squared plus 2 all times dx. Okay, I'm going to massage the function on the inside and then plug it back in. Consider the x minus 1 all squared plus 2. If you open up that bracket, that will give me x squared minus 2x plus 1 plus 2. All right, square the first. 2 times the first times the second, 2 times x times minus 1 is minus 2x plus 1. So therefore the function y is equal to x squared minus 2x plus 3. So therefore the area would have been the integral between 0 and 2 of x squared minus 2x plus 3 all times dx. And at this point we should be pretty good at using the rule for differentiating a polynomial in the form ax to the n. This gives me x cubed upon 3 minus 2x squared upon 2, which is just x squared, and then plus 3x, evaluated between 0 and 2. Let's plug in the 2 first. This is 2 cubed upon 3 minus 2 squared plus 3 times 2. That's the upper limit. Now in this case, when you plug in the lower limit, because each part of the function has an x in it, you'll get 0 there, 0 there, and 0 there. So in this case, you get 0 right through. But don't assume. You should always check it. Okay, so let's see what I'll get. Minus 2 squared is 4. This is area is equal to 8/3. And this is minus 4 plus 6, which is plus 2. 14/3? Yes. 2 is 6/3. 8/3 plus 6/3 is 14/3. And therefore, I can write the area as area is 14/3 units squared. So it's pretty consistent in the way the rules apply. Okay. The next one. Now, in the next two examples, you would notice that they didn't give a graph. It's always a good idea to know what the graph looks like so that you could correctly identify the region and the area in which you're working, the area for which you've, so you can clearly identify the region whose area you're trying to find. So these two, I didn't draw the graph, so we'll draw it on the fly. We should have curve sketching skills that would allow us to draw this graph, 4 minus x squared. That's a quadratic equation, and basically we just need to know where the roots are and if it's a maximum or minimum parabola. That's a maximum parabola because the coefficient of x squared is negative, and to find the roots, you put y equal to 0. So y is equal to 4 minus x squared. When y is equal to 0, you get 4 minus x squared is equal to 0. That's the difference of two squares. You can do it that way. 2 minus x times 2 plus x. 2 minus x times 2 plus x is equal to 0. From which we can say x is equal to 2 and x is equal to minus 2. And the curve, this y equal f of x, is a maximum parabola. So, even though these are would mostly be in the first quadrant, I still feel you should draw the graph. And certainly for the other integration tutorials coming up, you'll definitely need to know what the graph looks like. All right, so let's see if we can sketch this quickly. What are we looking at here? All right, we know 2 and minus 2. And where do they want it from? What? I'll double check this one. Between 0 and 4. I think it's 0 and 2 for this. I'm pretty sure. But I'll check it back. We can do between 0 and 4, but that would be inconsistent with what I'm trying to do in this tutorial. The curve actually is a maximum parabola cutting at 2 and minus 2. Let me get rid of this. Wrong set of axes. I need these. There. Alright, yes, I don't need an elaborate curve here. Okay, so this is gonna cut at 2 and minus 2. So let's say minus 2 is somewhere over here and 2 is over there. Maximum parabola is going to do that. Yes. I want the area between 0. I'm pretty sure it's between 0 and 2. This particular problem. Just so that you know, you can find the area between 0 and 4. But that's not what I'm trying to show in this particular tutorial. Okay, here's the curve. Y is equal to 4 minus x squared. Here is 0. Here is 2. So it looks like if they're asking me for this region there. How do I find that area? I integrate. The area is equal to the integral of f of x dx between a and b. Area is therefore equal to the integral between 0 and 2 of 4 minus x squared dx. If I were to integrate that, I will get 4x minus 1/3 x cubed. Yes, x cubed upon 3, or 1/3 x cubed, evaluated between 0 and 2. Okay, if I plug in my upper limit first, I'll get 4 times 2 minus 1/3 times 2 cubed. If I plug in my lower limit, I will get 0 everywhere. So let me reinforce that by putting the 0. So this is 8 minus 8/3. 24 minus 8 is 16. 16/3. So that area that you're looking for is 16/3 units squared. 24 minus 8 is indeed 16. Okay. Let's move on to the next one. This one says, find the area enclosed by the curve y is equal to 5 sine x, the x-axis, and the lines x equal pi upon 6 and x equal 5 pi upon 6. Okay, again, even though for this particular tutorial, your area is going to be in the first quadrant, you should still sketch the graph to see what it looks like. So let's sketch. Okay, what are we looking at? It's the sine curve, and it's multiplied by 5, which means, hold a second, there. I need my axis to be longer. Anyway, so the sine graph will look like this, times 5. Make it a little bigger. This other piece I'm not so much interested in. 1, 1, 2, 3, 4. 1, 2, 3, 4. Yes, this is 0, this is pi, and this is 2 pi. That's the sine graph. I'm sure I've done this with all of you guys. Sketch these curves. And I want the area bounded, and this highest value in this curve is going to be 5. Just some extra details. Wouldn't affect whether or not I can find the area. But it's good to know what the curve looks like I said. 5 sine x between pi up and 6. So pi up and 6 is somewhere over here. And 5 pi up and 6. Well, that's before I get to pi. So somewhere over there. So I'm looking at this region in there, finding that area. Well, again, area is equal to the integral of the function of x dx between a and b, which in this case would be the integral between pi up and 6 and 5 pi up and 6 of 5 sine x dx. Okay, what do we do? Integrate. When you integrate the sine function, remember you get the minus cos. So this is 5 times minus cos x, evaluated between pi up and 6 and 5 pi up and 6. I'll put the minus minus 5. I'll put the minus in front of the 5, so it's minus 5 into cos x, evaluated between pi up and 6 and 5 pi up and 6. Area is equal to minus 5 cos of 5 pi up and 6 minus cos of pi up and 6. Now, cos of 5 pi up and 6, let me double check these, but off the top of my head, I think this is minus root 3 upon 2. Let me see, I'm in radian mode. Am I in radian mode? Looks like I'm in radian mode there. Grad, degree, radian, yes. Let's go. Cos of 5 pi divided by 6 is equal to minus root 3 over 2. That's correct. So this is minus 5 into minus root 3 upon 2. And then minus, and cos of pi upon 6, I think that's positive root 3 upon 2. Cos pi. Yes, 0.866 decimal, but root 3 over 2. All right, so this area is equal to minus 5 into, and minus root 3 upon 2 minus another root 3 upon 2 is just minus root 3. And it's like minus a half root 3 minus another half root 3 is minus a whole root 3. So minus root 3. And of course, minus and minus gives me a plus. So this ends up being 5 root 3. And therefore the area is 5 root 3 units squared. Them apples nice, boy. All right. All right. So you get the general idea as to how to find the area under curve. Like I said, for the most part, you should know what the curve looks like and what the region is, whose area you're trying to find. And it's a basic integral at this level. Okay, let's move on to volumes of solids. Call it a solid of revolution. The question is, what is a solid of revolution? Solid revolution is obtained or is formed when the area bounded by a curve and specified limits is rotated completely. That means through 360 degrees or 2 pi radians about a specified axis. For this tutorial, for this video, we're only going to be rotating the curves about the x-axis. The rotation will only be about the x-axis. So makes our lives kind of simple. So let me show you some examples. I kind of drew the examples I wanted to show here, but I'm going to draw them over bigger and you know, make them look nice. I'll do over each one. All right. So the first one, let's see. Let's try this again. Yeah, the first one, I'm going to take a curve that looks like this. There's the curve. And here are the limits between here and here. I'm going to take this area. Remember, it says the solid revolution is formed in the area bounded by a curve. That's a curve. And specify limits. Well, my limits are between 0 and some value a, let's say. I'm going to take that area and completely wrap it around the x-axis. Right? What would happen is that the x-axis now becomes a line of symmetry, and the solid will look like this. There. Right? Just think of taking that area and wrapping it around the x-axis. It looks kind of like a bell. Let's try a couple more shapes. I'm going to take this sine graph, just this portion right here. There's the other half going there, but I'm not interested in that. I'm going to take this piece, the area bounded between the x-axis and the curve, between 0 and pi. This is pi. And wrap that completely around the x-axis. What would I end up with? Something looking like an American football or a rugby ball. Your objective is to find the volume of that, of each of those shapes. Let me do one more. I'll do actually two more. Yes, let me take this off because I don't need this anymore. Let's try another one. I'm going to take this curve, that curve right there. This could be y equal x squared for all you know. And take this region and wrap that around the x-axis. And if I wrap it completely around the x-axis, I get a shape looking something like this. It's looking more like a funnel. There. That's my volume. Or that's my shape. Now, this is rotation about the x-axis. This is rotation about the x-axis. This is a rotation about the x-axis. I'll just do one example. It's not required for this course, but at least you get the idea of how you wrap the curve around it's not required for this video, I should say, not for this course. You can get an idea of how you actually wrap it around the specific axis. I'm going to take one and rotate it about around the y-axis. So let's see what's that gonna look like. That's gonna look like. Okay, I'm gonna take this same curve that the last one I did, this one here. But I'm gonna take this region and spin that around the y-axis. Can you visualize the shape you're gonna get? Well, let's see. Looks like a nice little bowl. Looks like a soup bowl. And your job is to figure out how much stuff you can pour in there. How much soup you can have in that last one. I'm getting hungry. Thinking about soup. Yeah, so this last one here, just one example showing what it looks like if you were to rotate about the y-axis. And like I said, for this video, you're going to be responsible for these. How do you find that volume of the solid that you ended up with? Well, I'm going to give you the formula. It can be proven, but I'm going to state it without proof in this case. For the most part, use the formula to your advantage, and you're good to go. All right. The volume of a solid of revolution sometimes it calls a solid rotation. The volume of a solid revolution about the x-axis is given by the volume is equal to pi times the integral between a and b, whatever the limits are, of the function of x, all squared. You got to square the function, dx. There. Memorize that and use it to your advantage. There, that's it. Volume is given by that. Well, why don't we just jump right in? Let me see the examples I have here. I have 3 examples. And each one shows the curve. Lucky y'all. So let's jump in and run them quickly, and then we're done. Okay. The first one. If you notice, let me make some space at the bottom here as well. You're taking that area shown there. Find the volume of the solid generated when the shaded region shown is rotated through 360 degrees about the x-axis. So you're taking the region between 0 and pi upon 2 for the graph y equal to root of sine x, and you're wrapping it completely about the x-axis. And clearly, the shape that you're going to end up with is going to be something looking like, come down far enough. Let's try this again. This is 1, 2, 3, 4 up. So 1, 2, 3, somewhere about there. Yeah. Okay. all the way down here somewhere. Maybe a little further down, you know. Come to you, boss. There. All right, let's see if this is gonna. No, this is not gonna work. There. And that's my shape, more or less. How do I find the volume of that? Looks like a goblet. Well, first we're gonna quote the formula. The volume of that solid is equal to pi integral between a and b of f of x all squared dx. And therefore the volume is pi integral between 0 and pi upon 2. Remember, those are the limits. 0 and pi upon 2 of, now you got to square the function. What is the function? The function is the root of sine x, right? F of x, let me write it here. F of x, or y, I call it y up there, I'll call it f of x here, is the root of sine x. Therefore, f of x all squared is root of sine x all squared, which is just sine x, buddy. So it's pi times integral between 0 and pi upon 2 of f of x all squared. F of x all squared is simply sine x dx. Pi, when you integrate sine x, you get minus cos x, evaluated between 0 and pi upon 2. I'll pull the minus and join the pi on the outside, so it's minus pi into cos x, evaluated between 0 and pi upon 2, which is minus pi into, and now I'll plug my limits, both limits into the cos x. Plugging in the upper limit, I'll get cos of pi upon 2 minus, and plugging in the lower limit, I'll get cos of 0, which is not 0, people. Okay, cos of pi upon 2 is 0. Volume is equal to minus pi into 0 minus, and cos of 0 is 1. So the volume ends up being pi units cubed. And you can leave your answer in terms of pi. You can always leave your answer in terms of pi, not a problem. Unless they tell you otherwise, it's okay to leave the answer in terms of pi. That's the volume. Let's look at the next one. Next guy. Find the volume of the solid generated when the shaded region shown is rotated through 360 degrees about the x-axis. Not a problem. You should be able to do this with no issues. Okay, let me give myself some space at the bottom. X. Okay. Well, again, if I were to take that shaded region and rotate it take that shaded region and rotate it completely about the x-axis. I'm going to put a shape something like, looking like this. There. And my starting limit, was it 1? I think it was 1. Man. One and 5. Yes. There. This is 1, between 1 and 5. Okay. So let's just run this one. This should be easy. Volume is equal to pi integral between a and b of f of x all squared dx. We know f of x or y was 1 upon x squared, right? So f of x all squared is equal to 1 upon x squared all squared. F of x all squared is equal to 1 upon x to the fourth. So I'll leave it like that for now. Therefore, the volume is given by pi integral between 1 and 5 of 1 upon x to the fourth dx. Everybody knows that you have to write that as a standard polynomial. So I'll write it as x to the minus 4, the integral of x to the minus 4 dx. And when I integrate that, I get pi into x to the minus 4 plus 1, which is x to the minus 3 upon minus 3. Yes, evaluated between 1 and 4. Now I'll pull out the minus 3 and make it join the pi. I get all my constants on the outside. Minus pi upon 3. What's left inside? X to the minus 3, which I can write as 1 upon x cubed, evaluated between 1 and 4. This gives me minus pi upon 3 into 1 upon 4 cubed minus 1 upon 1 cubed. 1 upon 4 cubed is 1 upon 4 16 is 4 64 minus pi upon 3 into 1 upon 64 minus 1. This is equal to minus pi upon 3 into 1 is 64 upon 64. So 1 upon 64 minus 64 upon 64 is minus 63 upon 64, I think. Minus 63 upon 64. The minuses will go. 3 into 63, I think that's 21. 3, 2, 6, 3, 1, 21. So this gives me 21 pi upon 64. And I don't think we can break that down any further. Units cubed. Volume of that shape is 21 pi. Blah. Is 21 pi upon 64 units cubed. I thought that's pretty cool. The last one, coming down to the end here. Battery is dying on me, so I'd better finish before my battery dies. The region bounded by the curve y is equal to the root of 3x minus 1. The x-axis and the lines x equal 1 and x equal 3 is rotated completely about the x-axis. Find the volume of the solid of revolution formed. Now, I drew a thing there. They didn't give a graph, but I'm going to show a graph. Wherever you can, you should always get an idea of what the shape looks like. So let's see if we can massage this appropriately. First, I'll get the graph so you can figure out what this graph looks like. Y is equal to the root of 3x minus 1. Excuse me. Okay, where does this graph cut the x-axis? Let me see. When y is 0, let's play around with this a little bit. When y is 0, I'll get 0 is equal to the root of 3x minus 1. If you square both sides, you'll get 0 squared, which is still 0, is equal to 3x minus 1. X is 1/3. So this graph is going to cut the y-axis at 1/3. there are no negative y values. This is 1/3, x equal 1/3. Because the x-axis is x equal 1/3. There are no negative y values. So you have to plug in values of x that are greater than 1/3, and the graph is going to keep rising like so. There. They want the area bounded by the curve of the x-axis. Lines x equal 1. Let's say a little further along the line, and x equal 3. This region here. I'm going to wrap it around the x-axis, and you get something looking barrel-like. There and down there. Come on. Yes, something like so and like so. This is between 1 and 3. 1 and 3. There. Okay. Let's run it. Volume is equal to pi integral between a and b, f of x all squared, dx. We know that f of x is the root of 3x minus 1. F of x all squared is therefore when you square that root, the root and the square disappear, you just get 3x minus 1. And therefore, the volume is equal to pi integral between 1 and 3 of just 3x minus 1 dx, which would be pi into, when you integrate 3x, you get 3x squared upon 2, minus you integrate 1, you get x, evaluated between 1 and 3. What does this give me? Pi times 3 squared is 9, 9 3 is 27 upon 2 minus 3. That's my upper limit, minus what I get when I plug in my lower limit, which is 3 halves, right? 1 squared is 1, so that's 3 halves minus 1. Oh, can I mental this? Let's see. 3 halves minus 2 halves is 1 half. 27 halves minus a half is 26 halves, or 13. 13 minus 3 is 10. 10 times pi is 10 pi. I'll check it back. I'm prone to making errors. 27 halves. Yeah, in the second bracket is 3 halves minus 1. 1 is 2 halves. 3 halves minus 2 halves is a half. So after this minus sign, you just get a half. 27 halves minus a half is 26 halves. 26 halves is 13. 13 minus 3 is 10. I think I'm right there. 10 pi. And that's how you find that volume. And I have some problems for you set up right there from the same Raymond Tulsi text. You run those. Again, let me remind everybody from both Add Math and Pure Math Unit 1. Y'all are responsible, both groups are responsible for these first 3 videos. All of them. The Pure Math Unit 1 group, y'all got a bunch of stuff. You guys summarized the ideas there. Bunch of stuff. Rules of integration. Yeah, you got all that stuff coming up. Don't worry. Before the end of the day, I'll have the 3 videos at least set up, and then I'll overlay the information for the 3 videos set up, and then I'll overlay the videos probably tomorrow. Today is what? Today is the 15th, Friday the 15th of May. All right. So this is the end of this video. And this is the end of the series of 3 videos on integration. This covers, by the way, this is all the requirement for integration for the Add Math group. everything you need to know in integration. So effectively, we've done calculus. At maths, we've done both everything on differentiation, everything on integration. All right, I'm going to stop this one here. I'm out.